Yeah, I don't know, we have no chair this morning, but now we have one. So yeah, it's my pleasure to welcome, and I hope I pronounced this correctly, Irene Waldspurger. But how would you pronounce it in French?
Waldspurger.
Waldspurger, okay. Irene Waldspurger from CNRS and in Paris. And going to talk about alternating projections for phase retrieval with random sensing vectors.
Does everyone hear me correctly? Yes, no? Okay. So today, what I want to do is to present you an algorithm that can be used to solve a family of inverse problems. So this algorithm is called alternating projections, and the class of inverse problems that it aims at solving is phase retrieval problems. So this class of inverse problems is a subclass of a larger family of inverse problems called low-rank matrix recovery problem. So as an introduction, I'd like to say a few words about this more general class of low-rank matrix recovery problem, hoping that it will give you some context to understand the specificities of the specific algorithm that I'm going to discuss after that. So, what is a low-rank matrix recovery problem? It's a problem where you want to recover a matrix, M. So let's say it's square, but it could be non-square. So you want to recover a matrix M with complex coefficients. So the matrix is unknown. And to recover the matrix, you have information under the following form. So you know that A of M is approximately equal to B. So A is an operator. Typically, it's a linear mapping from the set of matrices to Cm for some M. And B is a known measurement vector. So typically, the regime that we are interested in is when the dimension of AM is much smaller than n squared. So if you have only the information that A of M is essentially equal to B, then the problem is very underdetermined. But you have an additional information. You know that the rank of M must be small. So you know that the rank of R must be smaller than some integer R that is significantly smaller than N. So with this rank constraint, you can hope that the underdetermined problem becomes well posed. And you can try to solve this problem for a given A, a given B, and a given R. But it turns out that in the worst case, these problems are NP hard. So we won't try to solve, so we usually don't try to solve all the problems of this class. Typically, we assume that there is some randomness on A, the measurement operator. And we want to design algorithms that work with high probability on A. So that will work for most measurement vectors A, but not all of them. So this class of problems has important special cases that you probably have heard of, at least the first one. So the first special case of this family of problems is matrix completion. So in matrix completion, you want to recover a matrix from a subset of its entries under the assumption that the matrix has low rank. So in this case, the measurement operator is the operator that to M associates the subset of entries that you can observe. And another special case is synchronization. So where you want to recover a vector, U, with complex coordinates. So you want each coordinate to have modulus 1. And you can measure for each k and L the product of UK by the conjugate of UL plus a large noise. So these problems have applications in imaging. So they are important, but so it's from this form, it might not be obvious why these problems can be seen as low-rank matrix recovery problems. But trust me, if you do a suitable change of variables, you can see that this is actually a low-rank matrix recovery problem. So typically, to solve a problem of this form, the first algorithms that have been used were non-convex heuristics based on the following principle. You write the unknown matrix M as the product of U and V, of U and V star, where U and V are matrices with only R columns. So if you write M under this form, then you know that automatically the rank of M will be at most R, so the rank constraint will be satisfied. So the only thing that you want to be satisfied now is that A of M must be essentially equal to B. So to obtain the satisfaction of this order constraint, you optimize the factors U and V using a reasonable criterion, and hopefully, once you've optimized for a long enough time, then the product matrix that you get satisfies the constraint AM equals to B. So these methods, they have the advantage of being relatively fast and easy to implement. However, when you naively optimize U and V, since the problem is not convex, it can happen that you get stuck in critical points. And so sometimes these algorithms, they just don't work. At some point, you stop making progress in the optimization of U and V. So to overcome this drawback, people have introduced convexification techniques. So the principle of convexification techniques is to replace the non-convex rank constraint by a convex approximation. So then you get an approximated convex problem. So the convex problem, you can essentially solve it in polynomial time. And if you're lucky, then the solutions of the approximated convex problems are the same as the solutions of the original problem. So the nice thing with this method is that you can prove that in a number of cases they succeed with high probability. So they work. But the drawback is that despite recent progress, they are usually slow, because you need to optimize over the whole matrix M, which has n square coefficients. So more recently, people have come back to the class of non-convex methods, and which are much faster, and they have tried to improve these non-convex methods so that they could establish success guarantees similar to the ones that we have for convexification techniques. So people have come up with the following family of algorithms. So these are algorithms that work in two steps. So you still try to write M, the unknown M, as the product of U and V star, where U and V have only R columns. So first, there is an initialization step where, using a carefully designed technique, you find hopefully good starting points U0 and V0. And then, starting from these points U0 and V0, you naively optimize U and V using a reasonable criterion. So it's very similar to the traditional family of non-convex methods, except that you have this initialization step. And in the second step, when you iteratively optimize the factors U and V, you get a sequence of estimates, and you hope that the sequence of estimates of U and V converges to something, and this something gives you the solution of your problem.
Here it's alternating minimization?
Not necessarily. It can be, but it can be first order methods. I'm going to say a bit more about it. So in a number of situations, what you can show is that these methods, they converge to the correct solution. So the sequence of estimates that you get converges to the correct solution. So these methods work. So it's what happens in matrix sensing, in matrix completion, so under some conditions and for some, under some conditions. And you can, in addition, show that in some of these cases, the initialization step is actually not necessary, in the sense that if you start from random starting points, then it still works. And this is the case again in matrix sensing, in matrix completion, and also in phase synchronization. So why, intuitively, how is it possible that these methods work? So first, let's consider the real two-step scheme, so the initialization step and the iteration step. So imagine that the way that you optimize the factors u and v is by trying to minimize some reasonable cost function. So here is the cost function that I consider. So it's not a convex function. However, it can happen that it's locally convex, or something like locally convex, around the global minimum. So if the initialization step gives you initial points that are close enough to the global minimum, then you start the optimization in the local convexity region, and everything happens as if the function was convex. You don't see the non-convex part. So if you try to minimize this function with the first order method, starting from this initial point in blue, then, although the function is not convex and has a local minimum, you will find the global minimum, because you have started close enough to the global minimum. So this explains why non-convex methods can succeed with a good initialization method. So now, how is it possible that it can also work without the careful initialization step? So it can happen that the cost function that you're trying to minimize, it's not convex, but it has no bad attractive critical point. So for example, look at this function. It's not convex, but its only critical point is the global minimum. So if you try to minimize this function with the first order method, starting from anywhere, then you will find the global minimum. And this is what happens in the problems that I've mentioned, matrix completion, matrix sensing. So actually, you're more or less minimizing an objective function that has no bad critical point. The consequence of these results is that there are problems that are a priori NP hard and that can be solved as if they were convex. So it's nice. And since these problems, they have interesting applications, we'd like to understand better why these methods works and which methods actually work. So typically, until now, the results that I've described, they have been established on a case-by-case basis. So each time you have a problem and an algorithm, you can try to study its convergence behavior, but we don't have much general theory. We don't know in particular which iterative optimization schemes you can allow in the second step of the algorithm that make the methods work. So typically, in almost all of the cases that I've described, the way the iterative step works is as follows. You fix a smooth objective function f, so a kind of cost function that is defined on the space of matrices, and that is usually a kind of square loss. So the square norm of the square norm of the difference between the measurement vector b and a of m. So possibly with some regularizer. You look at the factorized cost function. So the f tilde, the mapping f tilde that to u and v associates f of u v star. And when you want to optimize u and v, you minimize this cost function f tilde by local search. So typically with a first order method like gradient descent, but you can also use alternating minimization. And so, as I said, there is not much general theory, but the little general theory that exists seems to underline the role of smoothness of the cost function f. So, by contrast, the algorithm that I'm going to present now, it's an algorithm that belongs to this class of non-convex methods. It is a two-step method with an initialization and an iterative optimization step. However, it does not fit into the framework that I presented on the previous slide, in the sense that there is no cost function defined on the space of matrices, there is no factorized cost function, and also the method is really non-smooth. And as a consequence, the algorithm that we get, it behaves somewhat similarly to the non-convex method that I've just presented, but it also has some differences. So what it seems is that when we use a careful initialization step, it works. So this is a common point with previous methods. But when we don't use a careful initialization, there can be bad critical points. And nevertheless, it seems that the algorithm works. So I'm going to present these results. The second part about what happens with without a careful initialization will be mostly numerical, because so I did not manage to prove a lot in this part. So in the rest of the talk, I will start define the algorithm that I consider, and of course the family of problems that I want to apply the algorithm to. And then I will discuss the results that I've mentioned on the previous slide. So I will show that when we use a careful initialization step, the algorithm converges. And when we don't use a careful initialization, I will discuss what happens. So the family of problems that we want to solve is the class of phase retrieval problems. So a phase retrieval problem, it's a problem where you want to reconstruct some unknown vector xu with complex coordinates from the modulus of a xu. So here A is a fixed matrix with m rows and n columns. So in this talk, I will assume that A is a random realization of a normal probability distribution. And the double bar, as usual, denotes the complex modulus applied coordinate by coordinate. So if n is the dimension of the unknown xu, and m is the number of rows of A, which I call the number of measurements, then so axu, it's a vector in Cm, and the modulus of axu, it's a vector in R plus power m. Typically, we're interested in the regime where the number of measurements m is of the order of the dimension n. Below this regime, it's not possible to solve this problem with any algorithm. Before going on, let's observe that for any complex unitary number alpha, if we multiply xu by alpha, then it doesn't change the modulus of axu. So we cannot hope to exactly recover xu. At best, we can hope to recover xu up to multiplication by a complex unitary number. We say up to a global phase. The motivations for studying phase retrieval problems come primarily from physics. In particular, these problems have applications in X-ray crystallography. So when you want to image a small thing, something that you can try is to illuminate the thing with a light beam, a focused light beam, and so the object diffracts the light beam, and you can record the diffraction pattern, and the diffraction pattern is actually, under some approximations, the modulus of the Fourier transform of the support function of the object. So if you want to reconstruct the form of the object, it's enough to be able to reconstruct a function from the modulus of its Fourier transform, which is a special case of a phase retrieval problem. So for these applications, phase retrieval problems have been studied from approximately the 50s. There are other more recent applications in audio processing. So I said that phase retrieval problem is a special case of low-rank matrix recovery problems. But maybe it's not clear because I said in phase retrieval we want to reconstruct a vector, while in low-rank matrix recovery problems we want to reconstruct a matrix. But it happens that if you do a suitable change of variables, you can see that a phase retrieval problem is equivalent to a special case of a matrix recovery problem. So here is how you do it. So the problem that we want to solve is to reconstruct xu from the modulus of axu. Then you can say that it's the same as recovering xu star, so the rank 1 matrix with eigenvector xu, from the square modulus of axu. And it happens that the square modulus of axu, it can be written as a linear operator of xu star. So you can write it as big A of xu star for some linear mapping A. So then you see that the problem is actually equivalent to finding a matrix M with rank 1 that is symmetric and such that A of M is equal to the square modulus of axu. So you can equivalently rewrite the initial problem as a rank 1 matrix recovery problem. So as a consequence, the algorithms that have been developed for phase retrieval problems, they essentially follow the general development of algorithms for low-rank matrix recovery problems. So in a first era, people used non-convex heuristics that empirically were shown to work in a number of cases, but that had no correctness guarantees. Then in the 2010s, some people have introduced convexification techniques that have correctness guarantees, but that are slow. And in the last 2 or 3 years, people have came back to non-convex methods, and they have tried to extend to non-convex methods the correctness guarantees that held for convexification techniques. So I want to present maybe the most well-known non-convex method that has been introduced. So it's called Wirtinger flow. It exactly follows the general principle that I've described in the introduction for non-convex methods. So you want to solve a rank 1 matrix recovery problem. So you want to recover M such that A of M is equal to something you know, and such that the rank of M is 1. So how you do it? First, you carefully choose a starting point x0 that is an approximation of the eigenvector of M. And then, starting from this initial point x0, you iteratively minimize a quadratic cost function by gradient descent. So if you use a careful initialization technique, it can be shown that this method works in the optimal regime. And if you don't use a careful initialization technique, so you use just a random initial point, then you can show that there is no bad attractive critical point in an almost optimal regime, and so the method also works. So these results are essentially the same as the general family of results that I presented in the introduction. So it seems fine. We have an algorithm for phase retrieval problems that works with high probability and that is fast. However, it happens that it seems that in practice, Wirtinger flow is not what works best. There are other algorithms that are more efficient. And also, it's not what practitioners use. So in the rest of the talk, I will discuss another algorithm that is very well known in the phase retrieval community, that is widely used. And that is also a non-convex method, but that uses a different iterative step. And so it behaves a bit differently than Wirtinger flow. So this method, as I said, is alternating projections, and it works as follows. So to derive the alternating projections algorithm, you use the raw formulation of a phase retrieval problem. So you want to reconstruct xu from the modulus of axu. The idea is that instead of trying to directly recover xu, you try to recover axu. Since the matrix A will be injective, it's okay if you recover axu, you can also recover xu. So recovering axu is the same as recovering a vector y, also with complex coordinates, that belongs to the range of A, because it must be equal to axu, and such that the modulus of y is equal to the modulus of axu. So this problem, the second one, is equivalent to the first one. And to solve the second problem, you have a natural heuristic. First, you choose an initial starting point y0. Then you know that y0, so y, the vector that you're looking for, must belong to the range of A. So you project y0 onto the range of A. Then you know that y must also satisfy this modulus constraint. So you project your current estimate onto the set of vectors that satisfy the modulus constraint. But when you do that, of course, you're not in the range of A anymore, so you go back to the previous step. You reproject onto the range of A, you reproject onto the set of vectors that satisfy the modulus constraint, and so on. So you do these double projections for potentially a long time. You get a sequence of estimates, yn, and you hope that this sequence converges to the solution that you're looking for, axu. So this is how it works. So the choose some initial y0, it's the initialization step, and then the double projection is the iterative step. If you want a picture of how the method works, you can see it as follows. So the method tries to reconstruct a vector axu that lies in the intersection of two constraint sets. So imagine that I have my two constraint sets, so one is in red, the other one is in blue, and the point that I'm looking for is the point that is at the intersection of the two sets. So to try to find the point, I start with an initial y0, I project it onto the first constraint set, then on the second one, then on the first one, then on the second one, and so on. And if I'm lucky, when I do this double projection, in the end, I converge to the solution. So this algorithm, it has several advantages. It's fast, it's easy to implement, and with this algorithm, it's easy to incorporate additional constraints. So for example, if you know that the signal that you want to reconstruct must be real valued, positive values, things like this, you can easily add it, incorporate it into the algorithm. So what we are going to see about this algorithm is that if you use a careful initialization step, then the algorithm works. And if you don't use a careful initialization step, then it seems that there are critical points, but nevertheless, the algorithm seems to work with high probability, which is a bit mysterious. So the result about correctness when you use a careful initialization step is as follows. So provided that the number of measurements is larger than the dimension of the signal multiplied by a large enough universal constant, if you choose the initial point y0 with a careful initialization procedure, such as the one introduced by Chen and Candes, then you can show that with high probability, the sequence of iterates that you get, so the sequence yk, it converges to the solution AXU at an exponential rate. So in particular, it converges. This inequality constraint is essentially optimal up to the precise value of the constant, in the sense that if m is much smaller than n, then you know that the phase retrieval problem is necessarily ill-posed. So whatever algorithm you use, it's not possible to solve it. So this theorem says that our algorithm essentially works in almost the optimal regime. So since it's an algorithm that is important in practice, there had been other people that had studied its convergence behavior, and so I'm going to be brief about it. These people had shown that the algorithm works, but in a more or less suboptimal regime. And so the nice thing with the theorem that I just presented is that it works in the optimal regime with a simple initialization technique. The idea of the proof is actually really classical. The principle is that we know that the initialization technique, it lands in a relatively small neighborhood of the correct solution. So this has been proved by Chen and Candes. And now what we have to prove is that the iteration step, so the double projection, it's contractive around the global solution, which means that if you start close to the solution, then at each double projection step, you move closer to the solution and closer and closer. And so you converge to the solution and you can control the speed of convergence. The main technical difficulty is that the iteration operator, so the double projection, is not a continuous operator. So when we want to use concentration inequalities, we need to be a bit careful about how we do it, but it's totally doable. And it shows the theorem. Similar techniques have been introduced essentially at the same time for studying related algorithms. So if you're interested, you can look at Zhang and Liang and Wang, Genakis, and Edler. So now, if you don't use a careful initialization step, what happens? So this picture shows, as a function of the dimension, how many measurements you need so that the algorithm works with 50% probability. So you see that clearly the number of measurements has to be proportional to the dimension, which is exactly the scaling that we had in the theorem. So there is no surprise now. So this is when we use the initialization technique described in Chen and Candes. And now suppose that instead of using this careful initialization technique, we just choose an initial point at random. Then the picture that we get is the red line. So you see that when you don't use a careful initialization technique, you need a bit more measurements so that the algorithm works. So the initialization step is not unuseful. However, when you use a random initialization, it seems that the algorithm still works in essentially the same regime as when you use a careful initialization step. So you still need the number of measurements to be essentially proportional to the dimension. So why? So a first attempt to explain this behavior is to say, well, maybe, as for the other non-convex methods that we've discussed in this talk, it happens that when you have enough measurements, there are no attractive critical points. So there are no points in which the algorithm can get stuck. And since you can show that alternating projections, they always converge to at least a critical point, if there are no critical points other than the solution, whatever initial point you start from, then alternating projections will find the solution. So maybe there are no attractive critical points. So we can try to prove this, and we can show the following results. We can show that when m is larger than n square up to a multiplicative constant, then with high probability, essentially whatever initial point you start from, your sequence of iterates converges to the solution at an exponential speed. But here we need the number of measurements to scale like the square of the dimension. And it's totally unrealistic. In practice, we never want to use such a high number of measurements, and if we could consider using such a high number of measurements, then they would be much simpler algorithms than alternating projections. So this theorem is actually essentially uninteresting. It shows that there are no bad attractive critical points, but in a regime that we don't want to consider. And nevertheless, so it's disappointing, but nevertheless, it seems that this theorem is essentially optimal, in the sense that when the number of measurements is significantly smaller than n squared, then it seems that there are bad attractive critical points. So I tried to test that. So I did numerical experiments, and I tried to plot, as a function of the dimension, the number of measurements that you need so that there are no attractive critical points with probability at least 1/2. So here it's linear because it's a log-log plot. And you see that essentially the number of measurements has to scale more or less like n squared. By comparison, the line m equaled n is here. So it seems that at least in the small dimensions, you need a number of measurements that is really proportional to n squared, or maybe something like n power 1.9, to get rid of the bad critical points. So in the regime where the number of measurements is proportional to n, there are probably critical points. And nevertheless, it seems that, as I've shown you, the algorithm works with high probability. So it's somewhat able to escape or ignore the critical points. So what I think is that there are bad attractive critical points, but they have a small attraction basin. So when you choose an initial point at random, then probably, so with high probability, you won't land in the attraction basin of one of the bad critical points. So you won't see these critical points. So a picture could be as follows. So I recall you that the alternating projections algorithm works by alternatively projecting a point onto two sets of constraints. So let's imagine that the first set of constraints is the light blue one, and the second set of constraints is the dark blue one. So you see that so the first constraint set has a small bump. At the center of this small bump, there is a bad attractive critical point. So if you try to run alternating projections starting close to this bump, then the method will fail. You will converge to the bad attractive critical point. But since the bump is very small, well, if you choose an initial point at random, probably you won't be close to the bump, and then you won't see the bump. And when you run alternating projections, you will find a point in the intersection of the two constraint sets. So this is what I think happens. However, I tried to prove it, and I did not succeed. It seems difficult to estimate the size of the attraction basins. So what I have is simply a conjecture, and this conjecture says so that with an optimal number of measurements, so when the number of measurements scale like the dimension of the signal, then with probability arbitrarily close to 1, if you choose the initial point of the algorithm at random, then the algorithm converges at an exponential speed to the solution. So numerical experiments clearly support this conjecture, but I don't know how to prove it. That's all.
Yeah, we have time for questions. Are there questions? Yeah.
I have a little question. So, some time ago, I got some information from this group in Göttingen. So they use some Douglas-Rushford non-linear methods for doing place retrieval. Are you related? I came a bit later. So did you relate to this work? Or? Because it seems as if these projections, so they have work on projecting on two type of convex sets by using, so kind of fixed point schemes.
Yes. So from what I know, in practice, there are two main methods that are used. So the first one is alternating projections, so what I presented, and the other one is a Douglas-Rushford-like method.
Yeah.
So this Douglas-Rushford-like method, it also relies on projections. So when you write the algorithm, it looks somewhat similar to alternating projections. So I hope that maybe some of the tools that I've developed for alternating projections could be adapted to the Douglas-Rushford method that you mentioned. However, it seems that in practice, the behavior of the two methods is somewhat different. In particular, in difficult cases, Douglas-Rushford seems to work better. And I think so. This behavior, I can clearly not explain it with the study that I did for alternating projections. So I think there are common points and differences.
Other questions? I have a stupid one because I may have just missed it, but see, I mean, you try to optimize, you try to find the multiplication of two complex vectors from the squared modulus, and I mean, how do you? I didn't see. Maybe I missed if there's some bound on the vectors itself. But how do you prevent that one goes to 0 and the other one goes to infinity? Because you technically don't have an a priori Lipschitz assumption on your function. So how do you ensure that this is actually not happening in practice?
So when you want to solve this problem, so typically when you want to solve this problem, since you know that the matrix must be symmetric, so the two factors must be the same. So you optimize both of them at the same time. So you keep them equal, so then it's not possible that one goes to 0 and the other one goes to 0. No, but your question makes total sense. When you try to, in the family of low-rank matrix recovery problems that I presented at the beginning,
They were not.
yeah, it's possible that the two factors are not the same, and then it's a problem to prevent one going to 0 and the other one going to infinity. But so then, as far as I know, typically what people do is that in the iterative step, they add a kind of regularizer that prevents this phenomenon.
Or some constraint, yeah, exactly. I was missing that one. Thank you. We have more questions.
Is there any result on the solution error? I mean, not about the modulus of A times X, but just the real solution X, the distance between real solution X and our calculated solution. Not about X, A times X times.
So when you use, so if I correctly understand your question, when you use a random Gaussian measurement matrix with high probability, if the number of rows is large enough, the matrix is well conditioned. So if you manage to recover AXU with a small error, then you will recover XU with also a small error. So there might be problems when the matrix A is not well conditioned, but I think when the matrix is not well conditioned, you necessarily have problems. So I think it's not a case that we consider, that we want to consider.
Any further questions? If not, let's thank Irene again.